Section. Introduction. We're going to delve into the world of large language models, LLMs, which are typically trained on a massive amount of text and then fine-tuned to follow specific instructions. It's crucial to know when we can trust the output of these models, especially when we're using them in real-world applications. For instance, we can use the model's trustworthiness as a signal to selectively generate answers based on how confident the model is about the quality of its output. Previous research has shown that the distance to the training distribution in the embedding space can predict the quality of the output for conditional generative models. However, applying this to LLMs is a bit tricky because their training distribution is too large to estimate, and extracting embeddings from well-integrated LLM systems requires a lot of engineering effort. An alternative approach is to estimate a language model's confidence in its output by calculating the sequence probability or the length normalized sequence probabilities. But research has shown that these sequence probabilities don't reliably rank the outputs by quality. One way to improve this is by using human feedback to fine-tune language models to better align with human-judged quality. This can result in better quality calibrated models. However, getting human feedback data can be expensive, so we're exploring how to leverage the self-evaluation ability of LLMs to improve quality calibration. Interestingly, despite poor calibration on sequence-level likelihood, recent work has shown that LLM token-level probability can be quite well calibrated on choosing the correct option of multi-choice question answering and true/false questions. This suggests that evaluating language models generation with token-level probabilities using an appropriate prompt format might be better for selective generation than sequence-level likelihood. In this study, we're focusing on getting a confidence score that is quality calibrated on free-form generation tasks. We propose reducing the sequence-level scoring problem to token-level scoring by designing different self-evaluation tasks and propose a variety of scores. We're not just interested in predictive accuracy, but also in evaluating models' quality calibration for use in selective generation. We show that our proposed confidence estimation significantly improves the quality calibration, and can be used to abstain poor quality outputs using the TruthfulCA and TLDR benchmarks. Now, let's talk about sequence likelihood. Given a question and an answer, we have a sequence-level likelihood score. Although this score is statistically meaningful, it has been shown that it is biased towards sequence length, i.e., models tend to underestimate sequence likelihood of longer sentences. An alternative score to use is the length normalized likelihood. Although sequence-level scores have weak predictive power, previous results show that LLMs are well calibrated on multiple-choice question-answer tasks and true/false evaluation tasks. This suggests the model has better calibration on token-level scores. Inspired by this, we propose to reduce free-form generation to multiple-choice and true/false evaluation tasks, in order to leverage token-level calibration to improve the calibration of free-form generation. To convert free-form generation to a multi-choice question-answer task, we first sample multiple candidate answers. For a given question, we sample a number of answers from an LLM. We tried using a prompt to instruct the model to generate multiple different answers all at once, but the quality of the batch-generated answers were not as good as sampling one at a time. Given a question and a set of candidate answers, we append alphabet characters to the answers and form it into a multiple-choice format. A straightforward score could be the softmax probability for the characters, which was used in previous studies. The selected answer would be the one with the highest softmax probability. However, there are a few issues with that score. First, the score could change as the position of the candidate answers change. A simple shuffle and average could do bias and correct for the scores. Second, unlike the pre-designed multiple-choice QA task where only one true answer provided, in the free-form generation there is no such guarantee that only one of the sampled answers is true. When more than one true answers are in the candidate list, the probability of the true is dispersed among the true answers. This is an undesired property for comparing across questions, since different questions could generate different number of true answers. Lastly, it is possible that when the model does not know the answer, none of the sampled answers is true. If only wrong answers are provided, the model will be forced to choose one from them, resulting in overconfident prediction. To mitigate that, we add none of the above as an additional candidate answer to give model a chance to reject the sampled answers. A higher score for this option indicates that the selected answer is less likely to be correct. So we use this as the confidence score of the selected answer. Note that the selected answer is still the answer with the highest score within the original answer set, excluding the none of the above answer. Section Summary. Large language models, LLMs, are often pre-trained on a vast corpus of text and then fine-tuned on supervised data to follow instructions. However, determining the trustworthiness of an LLM's output is crucial for safe deployment. Previous research has shown that LLM token-level probabilities can be well calibrated for selective generation tasks, and in this study, we propose reducing sequence-level scoring to token-level scoring by designing different self-evaluation tasks. This approach significantly improves the quality calibration of LLMs and can be used to abstain from generating poor quality outputs. Section. Sample and eval. Reduce free-form generation to true, false evaluation task. We're going to simplify the process of generating free-form responses into a task of evaluating true or false statements. This means we'll take a question and an answer pair and evaluate them using a point-by-point format. We'll ask our model if the proposed answer is correct or not, as illustrated in a figure. Since this task is essentially a binary classification task, we can normalize the output score into a probability using a function called softmax. This approach is similar to the p-true method proposed in another study. That study also suggested including potential answers in the prompt. However, their focus was on the scaling law of the score's calibration, and they didn't compare it with sequence-level score and sample and select score. We're going to combine the best aspects of two methods, sample and select and sample and eval. Each of these methods has its own strengths and weaknesses. In sample and select, even though the unnormalized logit is better than softmax probability for calibration purposes, the logit score still depends on the other potential answers. For a fair comparison across question and answer pairs, a good score should measure the confidence in the pair itself, not depend on other potential answers. The sample and eval score is indeed independent of other answers. On the other hand, sample and select allows us to compare different answers and select the best one. So, we're going to use sample and select to choose the best answer for a given question. The answer with the highest softmax probability score is selected. After selection, we discard the score because it's not good for comparing across different questions. We then score the selected answer using sample and eval. If we add a none of the above answer, we penalize the confidence score with the uncertainty score for the none of the above answer. We call this combined strategy sample and select and eval. Now, let's talk about how we evaluate the selective generation. Suppose we have a dataset containing a certain number of questions to evaluate. For each question, we randomly sample a number of answers. We assume that the correctness of each answer is available, either through human evaluation or an auto-evaluation model to approximate human rating. Given a confidence score function measuring the confidence of a question and answer pair, we want to evaluate how well the score could be used for selective generation, besides the accuracy. Accuracy is evaluated by whether the score can be used to choose the best answer among the candidate answers within a given question. For selective generation, we compare across questions. Given the question and its selected best answer, we would abstain poor quality pairs to ensure better overall generation quality. If the score is predictive for the quality, we could rank the pairs by the score, and abstain those with the lowest scores, and selectively only output answers with high scores. For the abstained low-quality answers, we could instead output, sorry, I don't know. An honest, I don't know, answer is better than a wrong answer. To quantitatively evaluate the scores on selective generation, we use calibration AUC and selective AUC. Calibration AUC is a metric for a binary prediction task where the binary label is the correctness of the answer, and the prediction score is the confidence score. Selective generation curve measures the correctness of the answer as a function of abstention rate, where the samples are sorted by the confidence score and samples with the lowest scores are abstained. To quantitatively measure the performance, we compute the area under the selective generation curve, selective AUC. We also want to distinguish our method from the expected calibration error, ECE. ECE is commonly used to measure if the predictive probability value matches the ground truth accuracy. However, for sequence generation, getting the ground truth is challenging. Also, ECE can only be applied to probabilistic scores. The confidence scores we propose are not necessarily probabilities, so ECE is not applicable there. In this study, we focus on a more general setting that applies to any confidence scores, assessing if the confidence score is predictive of the output quality. Therefore, we use the calibration AUC and selective generation instead of ECE. Section Summary. The section discusses the evaluation of free-form generation models using a true, false evaluation task and pointwise evaluation format. The authors propose a hybrid strategy called sample and select and eval that combines the advantages of both methods. They introduce the concepts of calibration AUC and selective AUC as metrics for evaluating the performance of the confidence scores in selective generation. Section. Experiments. In our experiments, we primarily use the PaLM-2 large model, a type of language learning model, LLM. For each question, we generate 4 potential answers and remove any duplicates to avoid spreading the probability too thinly. We also evaluate the GPT-3 model, but due to limitations with the OpenAI API, we can't fully assess all methods or get complete results for GPT-3. Furthermore, we can't evaluate methods on GPT 3.5 and GPT-4 models because the OpenAI API doesn't provide output log probabilities for them. We use 2 benchmark datasets in our study. The first one, Truthfulca, is designed to test a model's ability to generate truthful answers against false beliefs or misconceptions. It contains 817 questions in the validation split. To assess the quality of the generated answers, we use the GPT Judge, a GPT-3 model fine-tuned on human feedback data. It has been shown that GPT Judge is 90 to 95% accurate in predicting human evaluations of truthfulness. The second dataset, TLDR, is a summarization benchmark dataset sourced from the Reddit website. It contains 15,240 examples in the test split. We randomly sampled 1,000 examples to save on inference cost. To assess the quality of the generated summaries, we use a reward model fine-tuned on human feedback data. The prediction accuracy of human rating of the reward model is 71.34%. Our results show that sequence-level likelihood doesn't perform well in terms of accuracy and calibration. It even has an AUC, area under the curve, below 0.5, suggesting that sequence likelihood is negatively correlated with correctness. Length normalization can improve performance, but AUC is still below 0.5. However, reducing sequence-level score to token-level scores via self-evaluation improves both accuracy and calibration over sequence likelihood. When considering all metrics, the hybrid strategy with the addition of a none of the above option performs best overall. Comparing 2 strategies, sample and select, and sample and eval, the former has decent accuracy but suffers on calibration metrics. Adding a none of the above option improves calibration. On the other hand, sample and eval performs better on calibration metrics but has slightly lower accuracy. This trend is more pronounced in GPT-3. Therefore, we propose a hybrid strategy to combine the best aspects of both. We also show that self-evaluation complements self-critique and revise, a technique to improve the quality of answers. We first apply this technique to improve each of the sampled answers, then compute the scores on the revised answers, instead of the original ones. On the revised answers, we see similar patterns that sequence-level scores are not well suited for selective generation, and token-level scores perform better. Self-evaluation improves calibration on TLDR summarization. We also assess the effect of position bias on performance. We compare the standard setting, where the answers are ordered by default, and the debiased setting, where the answer scores are averaged across all possible permutations. The difference in performance is not significant. Given that the debias process through shuffle and average is computationally expensive, we use the standard setting by default. In terms of related work, the calibration of LLMs on multiple-choice question-answer tasks has been studied. These studies show that sequence-level probability is worse than token-level probability for predicting correctness. However, these studies use multiple-choice question-answering datasets where the answers are predefined and not generated from LLMs. Our work focuses on the calibration of free-form generation tasks. We transform free-form generation to a multiple-choice task by generating answer candidates by itself. In terms of estimating language models' confidence or uncertainty, some propose to ask the model to express uncertainty in words along with the generated answer. However, It is shown that LLMs often exhibit a high degree of overconfidence when verbalizing their confidence. Others propose to use semantic entropy among a set of sampled answers to estimate models' uncertainty. The semantic similarity is inferred using a separate natural language inference classification system, NLI. Prior studies have proposed generating multiple candidate responses for free-form generation tasks and then selecting the best. The final answer is selected using a variety of methods. However, the focus of most prior work is on improving accuracy, not on confidence estimation or calibration. Our work is similar in the sense that it not only proposes to generate multiple options and then ask the model to choose one, but also estimate uncertainty to ask for clarification. However, we focus on more general question answering. Section Summary. In our experiments, we primarily use the PaLM-2 large model and sample 4 answers at temperature 1.0 for each question, deduplicating them to reduce probability dispersion. We also evaluate the GPT-3 model, but due to API limitations, we cannot evaluate all methods or obtain complete results for GPT-3.5 and GPT-4 models. We use benchmark datasets like Truthfulka and TLDR for evaluating the quality of generated answers and summaries, respectively. The results show that sequence-level likelihood is not effective for accuracy and calibration, but a hybrid strategy combining token-level scores and self-evaluation improves overall performance. Additionally, we find that self-evaluation is complementary to self-critique and revised techniques for improving answer quality. The effect of position bias on performance is not significant, and previous work has focused more on accuracy rather than confidence estimation or calibration. Section. Discussion. In our discussion, we found that general sequence-level scores aren't the best fit for selective generation. In fact, they can even negatively impact the quality of free-form generation. However, we've discovered that asking the model to self-evaluate can help reduce these sequence-level scores to token-level scores, which in turn enhances the quality calibration. It's important to note, though, that this self-evaluation process does increase the inference time by 1 or 2 times, especially in hybrid mode. Instead of this after-the-fact method, we're considering ways to enhance the quality calibration of the sequence-level score during the training and fine-tuning stages. This is a key area of focus for our future work. We'd like to express our gratitude to our colleagues at Google DeepMind, Denny Zhou, Zelda Marriott, Sharat Chikarer, Jasper Snowick, and Alexander Demore. Their insightful discussions and valuable feedback have been instrumental in this work. We're also grateful to Lyric Doshi, Shuizhi Wang, and Michael W. Dusenberry, also from Google DeepMind, for their technical support.